When you hear empirical formula, I want you to think of one thing: smallest whole number ratio. So what we're doing with the empirical formulas, and this is a little bit different than the next time that we speak when we talk about molecular formulas, this empirical formula is the smallest whole number ratio. So whenever you find out how many moles of each of the substances that you have or each of the elements that you have, we want to make sure they're the smallest whole number ratio. So there's a nice little sequence in doing that. The nice thing too is that when you look on your periodic table, all these masses represent what? 1 mole of that substance. So if I were looking at aluminum, if I had 1 mole of aluminum, then it would be 26.98 grams. So what we'll be doing is we'll be given either percentages or you'll be given some actual gram amounts, and that was one of the reasons why I had you do percent composition the last time that we spoke, is because most of the time, or some of the time, that you're going to be given percentages, and we can do or work with that to find out the smallest number of ratios. And it'll really make a lot more sense once we start to work these out. They're not very difficult if you remember the sequence. So let's see here. I think this is an example showing how to do empirical formulas. So let's look at the first practice problem, which says determine the empirical formula for a 400 gram sample containing 31.5% cobalt, 34.28% sulfur, and 34.22% oxygen. Now, there's a couple ways to work this out. There's actually a smart way, and then there's the long, more adventurous way. Where you see 400 grams here, in my mind, I don't see it. The reason why is because I'm given percentages. So if you're given a percentage, we're going to find out that the number of moles, or the ratio of those moles, are the same whether I use percentages or actually find out what the actual percent is, or how many grams I have within that 400 gram sample. So this 400 grams is actually a distractor. And you'll see it in some of the questions, you won't see it in some of the others. So if you are wanting to be efficient, what would be a good mass sample to work with if you have 31.5%, 34.28%, and 34.22%? What would be a good gram sample to work with? 100, yeah. So going and finding out how many moles is in each of these is an extra step. Now you can do it, it's just going to take you a little bit longer, except I know that during tests that you're a little more interested in finishing quickly. So let's go ahead and change these percents into grams, and also whatever order that the elements are given to you, keep them in that same order. So what we're looking at is we're looking at a cobalt, sulfur, and oxygen compound. And what the empirical formulas are allowing us to do is find out what these subscripts are. So we don't know what the subscript for the cobalt is, the sulfur, or the oxygen. That's what we're going to do. We're going to find those values. So let me go ahead and move that over here, and we can look at that here in a second. So we're going to find out what those values are. So let's go ahead and look at the 31.5% of cobalt, but I'm going to make that out of a 100 gram sample, which means I have 31.5 grams of cobalt. One nice thing about the periodic table is that even though all of these elements have different masses, they all gravitate toward one unit, which is 1 mole. So even though cobalt has a molar mass of 58.93 and say boron has a molar mass of 10.81 grams per mole, if I look at these two elements and say, okay, if I have 6.02 times 10 to the 23, I have the same number of particles, or I have the same number of things there, except the masses are a little bit different. So we always want to go to moles in this case. So if I have 1 mole of cobalt, and what was the molar mass? I didn't look at that. 58.93. So I put my 58.93 there. And that'll give me a number of moles. Okay, and then I'll do the same thing with the sulfur. So sulfur is 34.28%. We'll make that out of grams. And the molar mass for sulfur is 32.06 grams, and we'll find out how many moles that is. And oxygen is 34.22% or 34.22 grams in this sample. And the molar mass for oxygen is what?
16.
Very good. What we do not want to do, don't get in the habit of making that a diatomic. And some of you are like, oh, oxygen, it ends in gen, so I'm going to make that a 2. Remember that when we're looking at the periodic table, we want one representative. So even though some of these things, like nitrogen, oxygen, fluorine, chlorine, bromine, so on, exist as diatomic when they're alone, on the periodic table, when we're finding out the mole ratio, we're looking at 1 mole of that. So that'll be 16 grams, not 32. Okay, so then we'll find out how many moles we have of each. So this one says 0.5345. And what we do not want to do is we don't want to round too much because that's not a final answer. So we're looking for a ratio, so we want to kind of take it out as far as we can. I'd say no less than 3 decimal places on something like this. 4 is good, but don't write like 8 or 9. And this one's like 1.0693. And if you're not getting the same numbers, and 2.13. Does that sound good for a lot of you? And let's say 88. All right, now, looking at those numbers, that looks a little confusing. I really can't look at these values here and decide what my subscripts should be. So if you're finding the smallest whole number ratio, what do you think we need to do now to get a ratio? What's a smart thing to do? Can you just look at that and determine what the ratios are? No, I can't either. So what I want to do is I want to find out what the ratio is by dividing each of these by the smallest number of moles. So in this case, that value there is the smallest of all of these. So that I can do in my head. That's a 1. 0.5345, and then we'll do 0.5345. Okay, so we're actually finding out what the ratio is by getting our values to the smallest whole number ratio. Now again, these have to be whole number values. So looking at that, is that a 2? So 2.0, there's 3 zeros there. So that is a 2. And that one is 4, 4.00. So here we go. So that looks a little better for us to understand. So what is the formula for this? CO S2, in other words, this is representing sulfur. That one represents cobalt, and then the oxygen is a 4. So CO S2O4. Now S2O4 is not one of your polys. All right. So don't freak out and go, what is S2O4? Yeah. Okay. So again, when looking at this, what we want to do is we want to, first of all, if you're given percentages, change them into grams, find out how many moles of each. Okay. And then you want to, don't stop there, because sometimes you might get some numbers that are like 2 point whatever, 3.5. So they look like normal numbers, but you still have to find out what that ratio is. So make sure that you divide all of these mole amounts by the smallest number of moles from your work there. Okay. All right, let's look at number 2. The question asks, what is the empirical formula for a 425 gram sample containing 69.94 grams of, percent of iron and 30.06% of oxygen? So again, this is more of a distractor than anything else. So we're looking for an iron oxygen compound, and we want to know what are these subscripts here. So again, start off with your percent, change it to, say that we have a 100 gram sample. So we have 69.94 grams of iron. And what's the molar mass for iron? 55.85. And then we also have 30.06 grams of oxygen. Again, remember that's just for a single mole of oxygen. You get some good numbers from there. So 1.25. And for the, so 1 point, is that 8, let's see, 788. Okay, so what do we do next? Yeah, so we'll divide it by this here. So 1.252, that is a 1. And then 1.252, which is a really strange number. So let's look at that. So 1.5, anybody getting that? All right, now, here's a situation that you're going to run across. If you see that you have a decimal like this, we can't just round it up or down. We have to actually do something with that value. You can't just go, let's make that a 2 since that's a 0.5. There are some benchmarks that you're going to try to go after. And these benchmarks look like this, where we have a decimal where it ends in 0, like in this case here, pretty close to that. Oops, sorry, put that back up. You'll have a benchmark that is, actually let's go with the decimals first. So 0, 0.25, 0.3 repeating, 0.5, 0.6 repeating, 0.75, and of course 1. Okay? So these are the decimals that are your quote-unquote benchmarks that you're trying to get to. And in most cases it's 0 or a whole number, like in this case here, but what we don't want to do is we don't want to leave it as a decimal. What's really nice is to change this into a fraction. So when we look at these, let me move this guy up. Okay. What we want to do is we want to change these actually into fractions. And of course 3/4. So really I would take the 1.5 and I'd say, yeah, that's awesome, but I really want 1.5. The reason why I want a fraction there is because to get rid of that fraction, I'm going to need to multiply both of these values by the value that's in the denominator. Okay. So if I multiply everybody by 2, does that get rid of my fraction down here? Yeah. And I'd also need to multiply the top by 2 as well. So what that's saying is, okay, now I have, how many irons do I have? 2, and how many oxygens does this represent? 1.5 times 2 is 3, right? So my formula would look like this, where I'd have Fe2O3. Now, we have to check something, and you should check it just to make sure everything's in line. So if you have Fe2O3, actually I might move that down here. If you have Fe2O3, what is this? What is the actual name for this? Well, what's the charge on oxygen? No, don't say any Greek. We have ionic here. What's the charge on oxygen? -2, and you have 3 of those, right? So what must the charge on iron be? +3, good. So what that means is I have iron, and does iron have more than one charge? Oh yeah, it's either 2 or 3. So iron, and what's the charge on this? 3, correct? +3. And oxide. Is that a legal compound? Absolutely, because we have oxide and iron has a legal charge. Now, if we would have done something like, okay, well, I'm just going to round that to make that a 2 and leave that as a 1, and say you had this, ooh. Okay, so that you had that, I don't know what that is, because if I were to balance this out, oxygen would have a -2 charge, and then iron, in this case, would have a +4 charge. Iron doesn't have a +4 charge. So you can check to make sure that the formulas that you're actually writing are legitimate. That is not legitimate. So if you're finding yourself wanting to say, I'm just going to take that 1.5 and round it up to 2, that would be bad. Okay, so this is bad. This makes the chemistry gods very sad. Don't do that. Okay? All right, so let's look at, and part of your homework is the 3's. Good news is this is still the same stuff. So you already have the blanks there. Still doing pretty much the same thing. Yeah. So let's look at another example. Another practice problem. Here we go. Number 1. Okay. Says when iron oxide, actually Fe2O3, and I should say iron 3 oxide. When iron 3 oxide reacts with 18.94 grams of aluminum metal, iron is produced along with 35.74 grams of aluminum oxide. What is the empirical formula for this aluminum oxide? Now you're sitting here going, what in the world is this question asking? And that's a good thing. In other words, when we look at this and it says, well, iron 3 oxide, we don't really care about that because the question wants to know what is the empirical formula for the aluminum oxide, correct? And again, you'll run across questions like this in your academic career, whether it's in here or somewhere else. So we have to pick out information that's important here. Here it says that we have 35.74 grams of an aluminum oxide. And it also says that this reacts and we have 18.94 grams of aluminum metal. So here's what we have. We have this aluminum oxygen compound, which we don't know the subscripts for. And it has a mass of 35.74 grams. Okay. Also, we have information about aluminum metal, and it says that it has a mass of 18.94 grams. So, what information do we not have? The oxygen, very good. But is it possible to find the oxygen? Subtract the 2, very good. So we have this aluminum oxygen compound that has this mass, and here's our aluminum. So we want to find the oxygen by taking the difference of those two. So what is that, 16.8? Okay. So once we have that information, now we can have some fun here. Fun, yeah. So we can ignore that. Actually, let's move this guy over. We're going to solve for that. So we're going to solve for this, and let's move this over. Oh wait, we don't want that anymore, do we? Nah, we don't want that. We want this up here, and we also want the mass over here. Go that way. Okay. Actually, I could probably use that. Let's put it over there. All right. So now we can. Okay. So we need to find out how many moles. And I know oxygen 16, aluminum 26.98. And let's get some numbers here. So 0.7. Say 0.2. So is that 1.05? Okay, so we have those values. What do? Good. So divide by the smallest, which in this case is this. So that's 1. We can easily do that one. And what does that equal? So like 1.5 something. Okay. So 1.5, but I'm not going to write a decimal. What am I going to write there? Good, a fraction. So 1 and 1/2. So I need to multiply both of these by 2. Again, whatever's in the denominator. Remember, denominator. And so I get these. And so what's my formula for this aluminum oxygen containing compound? And you already knew that, right? Because you know that aluminum has what charge? +3, oxygen, -2. So you're like, why is he doing this? We all know that aluminum's going to be Al2O3. So let's look at the last example. Okay. It's just checking to make sure you're good. So if you were to run across a problem like this, be sure to show your process. I know you know what the answer is. At least some of you knew as soon as we started working out the aluminum oxygen. You're like, that's plus 3 minus 2. I know. Some of you are like, how do they know that? It's all right. Number 2, the last example here. It says propane is a gas commonly used for cooking and heating. Awesome. It contains the elements carbon and hydrogen. That's important. When 72.06 grams of carbon reacts with hydrogen gas, 88.06 grams of propane is produced. What is the empirical formula for the propane? So again, we have this carbon-hydrogen compound. So we're looking for the subscripts for these things. And some of you know what propane is, and that's fine. Nothing wrong with that. So we have this carbon-hydrogen containing compound over here. And what is the mass of this? Very good. So we have 88.06 grams. So we love word problems, being able to find out the fun information in there. Also, what else do we know? 72.06 grams of carbon. Great. There we go. So 72.06 grams. So that means that we need to find hydrogen, right? So hydrogen has a molar mass of what? So the difference between that, what is that, 16? Yeah. See, that we can do that mental math. That's easy. Okay, so this we don't need anymore, the 88.06. Okay, so you don't want that. Let's get this out of the way. We're going to be looking for that here in a moment. Actually, go ahead and work on this. Don't peek up. Try this one on your own. Yeah. You guys are gross little veterans by now with this. And again, don't round too much. Is that 15.873? Is that what you guys are getting? That's a crazy number. All right, so from here, what do we do? Divide by 6, good. Okay, so that's a 1. Look at that showing off there. And this one's going to be kind of 2.64, 6455. Okay. Anybody else get that? Okay. Kind of an interesting decimal, isn't it? However, going back to our benchmark, where is it closest to? Yeah, so, sorry, that should be 0.6 repeating. So 0.64 is very close, and I mean very close to the 0.6 repeating. Now, here's something that I wouldn't do to you. I wouldn't give you a problem where your decimal will come up like 0.29. That would be bad. Okay, that's like right in the middle of a quarter and a third. However, there's a long distance to go between 0.5 and the 0.75. So 0.64, that's very, very close to what fraction? 2/3. So that's what we're going to go with. It's very close, so that's safe for us to say that that's 2 2/3. So what are we going to multiply everybody by? 3. Very good. So you multiply that by 3, multiply that by 3, so we get the top number is 3. What's the bottom one?
2.
No. Not 7. Use your calculator. 8. Very good. Whew. Okay. So again, that's why God made calculators for you. So we have C3H8 is propane. Okay. The homework, the 3s and the 4s are your homework.